Okay, class. Wanted to put a little example out there for you too as well. This came up in office hours. So a couple of the students were having trouble with the program, the part of the program that was about the outlier detection. And again, you were provided with the code. The exercise is to add comments to what's happening inside of that code. The core of this with the outlier function and the OL and the OLS functions, those two functions, is it's actually a recursive function. That's the core of it. Recursive functions can be a little difficult to understand, so I thought I should give you an example of how one works to kind of help you with the coursework assignment here. So let me know in the discussion board or in email or come to office hours on Thursday. Let me know if this is still a little bit unclear, and we can walk through other examples of it. But basically here, this is going to be a recursive function example. This is a classic use case for where you would do this. And so what we want to try to do is we want to try to build a function that does this. So like if you give it a number, in this case, let's say 3, it'll take 3 times 2 times 1. It should come up with a number of 6. It's doing a factorial, okay? This is quite useful, and you'll find it all over the place in R for optimizing routines. So you may develop something and you want to try to make it go faster. By doing a recursive function, you can actually make this go faster. So let me kind of walk you through the code and what it's doing. So first of all, in this example here, we've got one called factorial recursion example. It's a function. It takes one parameter of x. X is a vector. It's a number. You would probably want to put some kind of a limit on it to say, a double precision or something along those lines. But just for this, we're going to use very simple examples. And you're going to see the larger that the example gets into, it's going to get into scientific notation. It becomes a little more tricky to read the output of it. First things it's going to do, it's got a series of if-else statements. Now you can do this as if-else, nested if-else statements, or you can do it as I've done it here, of having an if and an else broken out. I did it this way to make it even more readable for you. First thing it's going to do is it's going to check to see whether the x that is being passed into the function is either 0 or it's 1. If it is, it's going to just return back out that number. Okay? So if it comes in, if it's a 0 or it's a 1, it's going to bail from the function right here, right off the bat. If it's not, so if you put something any more than 1, the first iteration through, it'll automatically fall down into this else. This else is going to then turn around and return a call back to itself. So this will just keep calling itself. But when it calls itself, it's going to take the x, which you're using, it's going to take that and multiply it past this recursive function, and then for the parameter, it's going to use x minus 1. So it'll continue to decrement over time. So again, a lot to throw at you at once. But let's say we did this example and we're using 3 for the x that we pass in. So factorial recursion example 3 turns around and it says, is this a 0 or a 1? No, it falls down here. It then turns around and calls factorial recursion example 2. It then comes right back here because now it's being called itself. It's calling again. Factorial example 2 calls the function factorial example 1. It's not a 0 or a 1. It calls itself again. It is a 1 this time, as it's gone x minus 1. Now it's 1. So it ends the recursion at that point. It returns out the x. So you start with a 3. 3 doesn't fulfill the first condition. It calls 3 times the function again, minus 1. That, in turn, starts with 2. 2 does not fulfill the first condition, so it calls 2 times factorial recursion 1. 1 does fulfill the condition, it exits. So if we run this example, let me go ahead and run this script. Now we've got the function that's built. Now let's run the example. 3 times 2 times 1 equals 6. I put the print statements here and here simply to show you 3, 2, 1, 6. So it did that correctly. Let's run another test example. So if we did it 4. So in other words, 4 times 3 times 2 times 1 should be 24. Oops, sorry. And indeed it is. Same with 6. This one should be 720. And 720. Now to give you just an example, if you use something larger, let's say 25, for instance, it's going to be a rather large number at that point. You can see it'll still do it, but when it gets down to the actual final result, it's going to be in scientific notation, and it's going to be a very, very large number. So 1 times 10 to the 25th power, it's going to be a very, very large number that you use. So the whole core of this, and again, the core of that particular exercise, is to call itself a recursion function by breaking down into smaller tasks, especially if they're repetitive tasks, such as this one. By reprogramming it in this way, it's much, 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 much faster. So that's a recursion example. I will provide both the code as well as this video out to an announcement. If you have any questions, please feel free, discussion forum, emails, or send me an email directly, and we can walk through again on Thursdays office hours at 7 o'clock Eastern Time on Thursday if you need further assistance on this particular question. Thank you. Have a good one.